But no, the reason I do your homework the way I do is I'm trying to give you a week to work on something while pushing you outside of your comfort zone. See how you adjust. Plus, it makes your brain make neat little folds. I know that there are some people who are determined to leave here with a smooth brain. But we're going to try to not let that happen. All righty. So we're working a problem of X-ray diffraction. Let's see. I had a typo somewhere. I think it's in the next one. Okay. X-rays of wavelength 2.63. And then what's that symbol? Mm-hmm. Nope. That is a length that you can write in terms of meters. That is the angstrom. So you've probably heard of angstroms. That's a symbol for it. And so angstroms, does anyone remember how that works out to meters? What would I have to put on the end of it? What's the metric suffix? It'd be 2.63 times 10 to the what? So that would be no. Trying to think what 9 zeros would get us to. Oh, okay. So you're saying 9 zeros in front of the two.
I
Because if it's in front of the two, then yes.
I won't. Let's pretend I.
Okay, so it's 10 to the negative 10th.
And
If you put it 9 zeros behind the 3 and you left the decimal point where it's at, it doesn't really do anything. But in front of the 2, you nailed it. So that's 10 to the negative 10th. We're going to be dealing with picometers too. What do we think pico means? 10 to the what? Minus 12. Some of them eventually you just pick up because you use them enough. Okay, so wavelength of 2.63 angstroms. The angle of the first order diffraction was 15.55 degrees. What is the spacing between the crystal planes, and what would be the angle for the second order diffraction? Now we have to know what first order and second order are. So let's look at our Bragg's law. We're trying to find D. That's the spacing between the planes. So if I solve this, D would be n lambda over 2 sine of theta. And so, of course, lambda is our wavelength. Now, what do we mean by first or second order? Let's go back up and look at this. Where do you think first order reflects from? Yeah, so your first order is going to reflect right off the front of the crystal. Where do you think second order reflects from? Yep, that's going to penetrate the crystal a little bit and hit the next plane. So look at this very, very closely. What do you think second order means? And then I'll tell you what first order means. What do I have to put in that equation for second order? It's on there staring. Nope, it's on there staring you right in the face, and you're going to kick yourself when I point it out. No, we already have lambda. We have the wavelength of the X-rays. There's something we don't have that first or second order tells us. Yeah. What's second order? N equals 2, so what's first order? Yeah, there you go. Okay, so our first order reflection, this is going to be, so that's N equals 1, so I just need lambda. 3.63 angstroms over 2 sine of 15.55 degrees. And D is going to come out to be, let's see how many different ways we can write this. 4.91 angstroms. 4.91 times 10 to the negative 10th meters. If I move to 491, that would be 10 to the negative 12th meters, or 491 picometers. Again, if the problem doesn't tell you what unit to end in, you can just end in the first one you get, like angstroms. But make sure you can navigate around all of these. Now, what would be the angle for the second order diffraction? All right, well, two d sine of theta. All right. So we want theta. So first, let's do sine of theta equals n lambda over 2d. But now I have to figure out how to get theta. I want to see if you can figure out what this looks like mathematically so you know what neat little button it is on your calculator. How do I get theta by itself? Inverse sine. So if I do that to both sides, I'll get theta, and then this side, I'll get sine to minus 1, which you will find that nifty little button on your calculator, and lambda over 2d. Who still has PTSD from Tim making them do math in their head? Maybe we should just have a test this semester where I was like, yeah, just no calculators. This semester, you'd have to do it with logarithms. Ooh. You do logarithms in your head? No better time than the present to try. Okay, so our second order is going to be n equals 2. And then our lambda is 2.63 angstroms over, let's see, 2 times d, which we just found is 4.91 angstroms. We punch all that into our calculator and we get 32.4 degrees as our reflection angle from the subsequent plane, the second order reflection. So that's why we put the 2 in there. So n equals 2. Okay, so that's Bragg's law. Now, when you actually do this in experiment, you start to get pretty little spectra like this. So you see all the different crystal structures there: calcite, quartz, gypsum, muscovite, calcium sulfate hydrate. So you're going to start, and what'll happen is the x-rays will go in, kind of a fun little machine. You have an x-ray gun that's on like a circular track, and you just hit go and it just goes around the track, constantly shooting x-rays at your crystal right in the middle. And so, at least that's one I use. Sometimes now they use the powder diffraction, but I use the old one. And you're going to, every time it hits, you're going to start to get these peaks that your sensor will read. And those peaks are in orders of 2 theta. So between figuring out that, figuring out spacing inside the crystal, because now you have your 2 theta angles, and the intensity of the peak, you can start to figure out what the internal structure of the crystal actually looks like. Remember that diffraction pattern I showed you had bright dots, less bright dots than dark spots? So that's what it's measuring on the y-axis, is intensity. So this is an actual experimental X-ray diffraction spectrum. So now that you're all ready to go to graduate school and do this, let's start talking about types of crystalline solids. All right, very delicious. So, type of crystalline solids. The first one is an ionic solid. These are all dictated by what is at the primary lattice points. So in an ionic solid, so you see you have sodium chloride, or you have a complex ionic solid in silver chlorate. What will you find at the lattice positions? What do you mean by lattice positions? Coulombic forces, you know what those are? Coulomb's law. It's a way you can actually start to judge lattice energy. So the higher the lattice energy, the stronger the crystals held together. And so it's Coulomb's law, it's an electrostatic force. And so it'll be charge one, charge two over R squared, which is the separation between the two charges. So the lattice energy will be governed by two things. So if you have a plus one and a minus one multiplied together, and a plus two and a minus two multiplied together, the plus two minus two is larger. But then you take into account ionic radii to see how big your R value is. Because if your R squared is too big and the radii are too large, that's going to weaken the lattice energy. So everything, you can really start to get an idea of the strength of a crystal lattice by using Coulomb's law. So in ionic solids, you have ions at all of the major lattice points. A lattice is going to be the structure which builds a crystal. The smallest version, the smallest unit of a lattice is going to be your unit cell. And so your lattice then will be that, basically like cut and paste over and over and over and over and over again. We have molecular and atomic solids. What do you think the difference between those is? Again, you see the dry ice show up again. There you see solid iodine and its unit cell. Well, then you see silicon dioxide and diamond. What's the primary difference between those two? Molecular solid, atomic solids. Oh, wait till you take biochemistry and you have to do amino acid crystals. In atomic solids, all of the major lattice points are taken up by atoms. Which is the molecular solids, you'll have molecules. You see in these two molecular solids up there, how you have an entire molecule at individual points. You can kind of judge it. Just look at one of the corners of the carbon dioxide cube. That entire corner is a molecule of carbon dioxide. Versus in one of these, your corners are going to be atoms and cells. One thing you're going to start to notice, let's look at our diamond here. There's one over there. Diamond ends up forming what we call a face-centered cubic unit cell. Oh, there's one. You'll see what that means in a little bit. We have network solids and metallic solids. We've already seen some network solids. Your silicon dioxide and diamond were network solids. Network solids have very strong directional covalent bonds. So directional covalent bonds means that they're going to be, the covalent bonds are bound to that location. Look at the metallic solid though. How does it bond? It's still a type of covalent bond. And then for a metallic solid, what is at each lattice point? So the metallic solid does form a type of covalent bond, but what does the metal do and what will that put at each lattice point?
Has to be positive.
It has to be positive. So the positive nuclei of the metal atoms will take up the lattice points. And then the covalent bond is going to be it's going to be a delocalized bond. And so essentially what you get inside the metal is it's almost like gas of electrons. And they're kind of floating all over the place. So all of the atoms are sharing all of the electrons. This is also why metals are such good conductors. Once those electrons delocalize, these can be polarized really easy. Then we have some like group 8A solids. These are going to be made from your noble gases. You see there on the top left, we have a xenon hydride, where the little ball structures are made from hydrogens, and right at the center of the hydrogens, you have xenon atoms. The other structure is an argon crystal. If you guys haven't had the joy of taking the time to read texts from Dog, then you're missing out. Oh, there's an entire, like these were a big meme for a good while, so there's a bunch of them. What would your dog say if you could text him? How are classes going? Is everyone staying unstressed? Don't tell me that that college is stressful. No. I always do tell people these jobs are impossible to get because it's like one person in the whole world gets the job. But I do know somewhere off Greece and then off Japan, there's islands called Cat Islands, where the whole population of the island are cats, and the government of the country will pay someone to actually live there and just take care of the cats. But it's like one person in the whole world. However, there is a dog ranch in South America. So there are jobs out there you can get if you ever just want to disappear, but they're hard to get. There was a time when I considered Cat Island, but there's so let's talk about the structure and bonding in metallic crystals. The two main ones that we're going to work with are hexagonal closest packing and cubic closest packing. This has to do with how the metal atoms stack inside the crystal. And they're governed by your hexagonal closest packing is going to be an ABA stacking. And your cubic closest packing will be ABC. And it's just going to, and what it does is ABA or ABC versus depending on how the atoms of each layer shift. And then it's just going to repeat this stack over and over and over again. So like your cubic one would be ABC, 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 just over and over, just building layers. Now, when you're solving problems, and you'll see what this means in a minute, your cubic closest packing is limited to face-centered cubic unit cell, okay? You're going to have 3 different cubic unit cells, but if you're dealing with a metal that is cubic closest packing, you are limited to the face-centered cubic unit cell. That is how the metal builds itself. All right, let's start talking about some of these unit cells. So both of these being the same thing. It just depends on which book you're reading. I wanted you to see both notations so that you didn't get confused later. You have a basic cubic unit cell, BCC, or a simple cubic cell, or SC. I do this because most textbooks you read are going to use abbreviations. The important thing you want to try to get your mind around is how many atoms are there inside of each one of these unit cells. Because, for example, if I know the number of atoms in a unit cell, I can tell you what the mass in that unit cell is. So, your basic cubic is only going to have atoms at the corner. But you have to ask yourself, how much of an atom is in a single unit cell? Well, you look here and you see an atom at that corner. What you notice is that that atom is shared between eight different unit cells, which means that each unit cell is only going to get 1/8 of an atom. And so if I'm asked how many atoms are in the basic cubic unit cell, I have 8 corners, each with 1/8 of an atom. So altogether, that's just one atom in the unit cell. I also want you to pay attention to something if you're asked, hey, like let's say that's your atom right there in the middle of your basic cubic unit cell system. How many neighbors does it have? Well, the way you figure out neighbors is you just go along the lines, not diagonals. So there would be a neighbor, there would be a neighbor, there would be a neighbor, there's one, there's one, there's one. So for example, that atom would have 6 neighbors. You're not going to go that way and count that one. You don't do diagonals. You just go along the straight lines. Let's talk about the body-centered cubic cell. Now, some of these, they try to name them intuitively. This one's called body-centered because you have one entire atom at the very center of the unit cell. So for this one, again, you have the 8 corners with 1/8 of an atom apiece. So the corners will make up one atom, and then the atom at the center of the unit cell is one whole atom. And so this unit cell has 2 atoms. They look like that every morning before coffee. It's me in my office trying to prep first thing in the morning at like 6 a.m. going, eh. It's kind of bad that I'm at the point where I drink something called Death Wish coffee. Oh, you can get it at Walmart. It's twice the caffeine of regular coffee. Our last one, we have the face-centered cubic cell. So remember, this is the one that you have to use if you're talking about a cubic closest packing model for a metal. This is the unit cell. Now, can someone explain to me why this one has 4 atoms? So first off, keep in mind, it's called face-centered because every face of the cube has an atom on it. And if there's an atom on that face, that means that that atom is split between 2 unit cells. So each unit cell will get half the atom. So why does this one have 4 atoms? No, that's the body center.
Corners make one with the size of it.
Right, so again, we have our corners. 1/8 of an atom on each corner, 8 corners, so that's 1 atom. Every face has half an atom. There's 6 faces. And so 6 faces at half an atom apiece gives us 3 atoms. 3 plus 1 gives us 4. By the time we're done with this, you're all going to go home, take off your jewelry with crystals on it and go, nope, I hate crystals. I'm done. Because the next thing we're going to do is some geometry. No, we need to figure out what the length of a side of the unit cell is. That's how you can figure out the radius of an atom. Okay. So let's just start with the simple cubic cell. All right, so I'm going to do there to there to there. And then I'm going to refer to the entire side of a unit cell as A. So that whole side is A. What do you think the length of the side of the simple cubic unit cell is? Those first lines I drew on there, what are those?
So, radius,
Each one of these is the radius of one of the atoms. As it goes from the center of an atom out to the edge, 2R. So that means A is going to be R plus R. The length of one of the sides of this unit cell will be 2R. Let's work on the face-centered cubic. I go there next because it's easier. So what I'm going to do is I'm going to make a right triangle. I'm going to go diagonal across the face of the unit cell. Then my right triangle will be right there and include the length of the side. Okay, so I know that that's A. I know this side is A. What about the center?
4R.
4R. You see you have an R, and R, and then a full diameter is 2R. So the way I do this, A squared plus A squared equals 4R squared. And then I can start solving for A. So that's 2A squared. That's 16R squared. A squared is 8R squared. And A will be the square root of 8R squared, or square root of 8R. So that's the length of one of the sides of the face-centered cubic unit cell. Now we'll do the one you're going to have to be able to see three-dimensionally. I just feel like you guys are having such fun in here. With the subtle looks of kill me now on your faces. Okay. Did you still need something off it? Okay, so we need to see this one three-dimensionally. I am going to make two right triangles this time in order to solve this. The first one is going to go back through the cube, up through the atom in the center, and it's going to diagonal the whole cube. So I hope you notice that that is a length of 4R. Because if it goes through the two atoms on the corners and goes all the way through the atom in the center, that's R plus R plus R plus R. Now, what I'm going to do is make a distance that I don't quite know yet. I'm going to put it there. The reason I'm doing that is then I can incorporate the side of the cube and I get a right triangle. But I also have a second right triangle. right there. No, that's not working. Yeah, whatever. I have a second right triangle right there, which incorporates A on each side. That's A. It's one in the center. It's for R. And then I'm just going to call this one on the side length D. Okay, so now what I can do is I can say, well, A squared plus A squared equals D squared. Does everyone recognize this? Okay, good. Yep. Just wanted to make sure that it wasn't something we skipped. And people are going, why the hell does he keep writing? Then my other one, my other triangle that goes back through the center of the cube is going to be A squared plus D squared equals 4R squared. And so now I can actually substitute D squared. A squared is A squared plus A squared. It's 16R squared. 3A squared. 16R squared. And then, of course, the length of our side. Going to be the square root of this whole thing. Whoa. Or 4 over the square root of 3R. So there's the length of the side of the body-centered cubic unit cell. So now we have equations relating the length of the side of a unit cell to the radius of an atom. Okay, so let's use this information to solve a problem. Aluminum has an atomic radius of 143 picometers and forms a solid having a cubic closest packed structure. So what unit cell is that? Cubic closest packed structure. So there's a couple of things I know. My face centered cubic, that's 4 atoms. Let's see. So then, of course, A, the root of 8R. So I know these things. Calculate the density of the aluminum. So we need it in grams per cubic centimeter. Okay. So first off, density, mass over volume. How do I get the volume of a cube? Side cubed. So that's going to be square root of 8 times 143 times 10 to the negative 12th meters cubed. And that's going to end up giving me 6.62 times 10 to the negative 23rd cubic centimeters. Now, what about the mass of aluminum in there? How can I figure out the mass of aluminum in the unit cell? I'm going to have to use the grams per mole from the periodic table. I mean, I'm going to need moles of aluminum in the unit cell. How am I going to get that? Nope, I'm gonna have to convert moles to grams. 4 atoms. So if I say I have 4 atoms, how many atoms do I have in a mole? Which is what number? Avogadro's number. 6.022, 10 to the 23rd atoms per mole. And then for aluminum, it's 26.98 grams of aluminum per mole, which is going to give us 1.79 times 10 to the negative 22nd grams of aluminum in a unit cell. So then my density, the mass over volume, 1.79, 10 to the negative 22nd grams over 6.62, 10 to the negative 23rd cubic centimeters. That is going to give me 2.70 grams per cubic centimeter. I want you to learn how to solve problems like this. You will see these on your ACS final. Okay. This is why it's important to remember how many atoms are in a unit cell. And did you think you were done with Avogadro's number? No. At least you're honest. You say no, but in your face you say, of course not. Why would we be? You're very honest people. Now, you guys take a few minutes and try to solve this one. An iridium crystal. Notice how this one straight out tells you face-centered cubic lattice. You're basically going backwards from what we just did. And we'll speed back up here pretty soon, but I usually slow down a bit for crystals since this tends to be pretty new material for most people. You know, running short on time. How close are we?
Not that bad, but
Well, I'm gonna start working through it and see how close you get. So we know our FCC is 4 atoms. Let's see, we know density is mass over volume. And solve for A cubed. M over rho, so the length of one side. And mass over density to the 1/3. So cube root. All right. You can get mass real quick. And then the iridium is 192.2 grams per mole. That will give us 1.28, 10 to the negative 21st grams of iridium. All righty. And then we need the side of our unit cell. All right, well, we can get the side. So now we'll do this. Our mass, 1.28. And then we get 21st grams over 2.6 grams per cubic centimeter. Cube root. That'll give us 3.84. 10 to the negative 8th centimeters. So now we know the length of the side of the unit cell. And then we know that the relationship to the side to the radius is square root of 8r. So r is going to be a over square root of 8. And what's all the ways we could write this? Well, r is going to be 1.36 and 10 to the negative 8th centimeters. Let's see. That also equals 1.36 times 10 to the negative 8th meters, or 1.36 angstroms. We could also do 136. Oh, hang on. That's not 8, that's 10. Negative 10, there we go. 136, 10 to the negative 12th meters, or 136 picometers, any one of those. So once we know our unit cell, we can just use our relationships, the atoms per unit cell to find mass, the relationship of side to radius. And we can figure out what we need to figure out for density of a metal. Okay. So who's over today? What videos? Oh yeah, yeah. That'll help. Organic Chem 2 is good.